Okay, we're starting the recording. That's good. Do you guys have any questions before we start from chapter 6 and chapter 7? It sounds like your test. It sounds like your test is going to cover mostly chapter 6 and 7, and then maybe a bonus on chapter 8.
Yeah, I'll just ask questions when they come up.
Okay.
Don't have one planned yet.
Okay. So I'll start on the first problem. This one is one that Twacha has given you guys, and we've seen before. He gave us this last semester. This is somewhat of an VMF problem right here. Number one. What we'll do first is we'll try to get some of the stuff from the problem. I think this one maybe goes a little bit too far. It asks for the capacitor and asks you to try to figure that out. I mean, it's not that bad to figure that out, but we can do that. So first what we can do is we can start writing down our H field or time harmonic H field. And since we want to get this in terms of B, what we can do is we recognize that B in this case is equal to mu H. Then with this, we can then just get rid of this. Luckily, this term right here actually gets canceled. So if we multiply by mu H, then we get 4 pi over 4 pi times 10 to the 7 times 10 to the negative 7, and it cancels out basically. So that's good. So that makes it easy for us to do in terms of the math involved. So then what we're left with is B of T.
And so mu equals 4 pi divided by 10 to the power 7?
Yeah, 4 pi 10 to the minus 7 is what mu equals. Well, maybe not the big 7. There you go. Yep. Then we just have B is equal to Z hat cosine of 120 pi t. And so an important thing to recognize too is that what we didn't know at the time is that this is a quasi-static representation. And so back in the semester that he gave this, he was trying to emphasize a lot about the quasi-static. And basically what that means is that you assume that there's no real change in the E field, right? There's no big change, right? Because we see that the frequency here is 120 pi t, right? So that's very small. That's 60 hertz, right? 60 hertz. So we're dealing with basically wall outlets here. What we can do next is then we can solve for the EMF. This is the critical part of chapter 6. He wants you guys to know about rotational, right, and transformer EMF. So this is just not really any motion, but it's the EMF through a loop. So what we can do now is we can write out our standard equation for EMF. We just have V EMF equals minus N ddt of the integral of B dot ds, which is the surface area, right? Okay, let's go back to the problem, see if we can try to fill some of these spaces in. So what we'll see is we're given a radius, right? So that's what we can do to help solve for the area. 5 turns, right? So it's just 5 times. So that's n. So n's right here is 5. We're then said it's placed in the xy plane, so we can draw a picture for xy, y, x, and you can kind of just draw the loop right here. You got z. Then we know this right here is in the z, so it's going up like this. Okay. And we'll worry about the capacitor plates in a little bit when we go to solve for the average power dissipated in the resistor, because we have to solve for the equivalence impedance. Okay. This shouldn't be too bad right here. We'll have minus 5, and then we have z hat cosine 120 pi, and then ds. So this is z hat, I believe Yeah, Z had ds, so it's just the surface area right here. Luckily for us, this right here is in the direction, so we can just get rid of the dot. Z hats are in the same direction, so you just have ddt minus 5. Then you have cosine of 120 pi t ds ddt. I'm forgetting some stuff, sorry. Okay, we can then solve for this. We can then get a surface area term right here, so it's just area. We'll then get minus 5. Cosine integral, that's easy. That's just sine, or excuse me, that's just sine. Yeah, what is it? What the hell did I do? Oh, I'm silly, of course. Here's, obviously this term right here doesn't get affected by ds, so we can just take it outside. We'll have to still leave the ddt here, but we just have ddt of cosine 120 pi t, and then we just have integral ds. Okay, ddt of this right here is where we actually get the minus sign. So then we have 5 sine minus sine. It gets rid of the double negative 120 pi t. So I just took the derivative of this and then multiplied it with the minus, and we got that. Then what we also have to do is we also have to worry about the inside as well. We then just multiply this by 120 pi. And then we also have this area term, which is just right here, area. Okay, now that we have our VMF, our VEMF, what are we supposed to solve for first? What we're supposed to solve for is the time-varying electric field intensity. So for this one right here, what we have to do is we have to set, we have to also recognize this as well. VEMF is equal to the closed loop integral of E dot dl. Luckily for us, since E of t really only varies with time, we can take it out of the integral right here, and we don't really have to integrate with dl. We can, we actually do have to integrate with dl. It's just 2 pi r. Then what we do here is we get VMEF equal to E, and this is the, I should have put the time harmonic, excuse me, E of t right here for completeness. And then we have this E of t, and then 10 pi. Okay, now what we'll do is we'll come back up here and we'll figure out what VMEF actually is. So we'll solve for this term right here. Like I said, it's just the surface area. I believe, are we given the, let's see, are we given the radius? Yeah, we are given the radius right here. So we're told it's half a meter. So then what we do is we do pi r squared for the area. Yes, pi r squared for the area.
How did you get the 10 pi, by the way?
10 pi, I believe I got that because, let me think here. I think what you do is you do 2 pi, is it, you do 2 pi r? Is that, okay, so.
Well, r is 0.5, so it would just become pi. That's all I was immediately thinking. That's what I was asking.
Isn't it because it's 5 turns and the circle's 2 pi?
Well, it would be pi, so I'm wondering how I got 10 pi here. I'm figuring that out. It would be 5 pi at least. Let me see here. But yeah, you have 5 turns, right? So your DL is 5 times around. So it'd go once around, once again, and once again.
So the DL we're integrating 2 pi n?
Yes, 2 pi n, yes, exactly. 2 pi rn, whatever, yeah. Number of turns. For the DL, yes, exactly.
Okay, so it's 5 pi.
Yep,
right.
Yep, it would be 5 pi then, yeah. Okay, then we'll solve for area again. I believe this is actually not the complete area term. This is just one total area turn. So this is just one time around the surface area upwards. Because n takes care of that for us. This is just pi r squared. R for us is half a meter, so it's 0.25 pi. This is just 1 over 4 pi. Okay. Then what we'll do is we'll just plug this all in and we'll come back. We'll plug this term in with this guy and we'll just write out the full thing so you guys can see 120 pi times 5 times 1/4 pi cosine, excuse me, sine of 120 pi t equals 5 pi e of t. Okay, what we can do is we can start canceling out some terms. So we have a 5 over here, we can cancel that out, we can cancel this out, a pi here, a pi here. Then we have 120 pi over 4, so that's just 30 pi. So we get 30 pi sine of 120 pi t. Let's see here. Yes, okay, 120 pi t. Awesome, okay. That is the first step for this problem. That's part A. Any questions?
Yes, just a confirmation on when we back up where we originally integrated the VMF, the negative and DTT integral the BDS. So for certain ones for that B value, we had Z's right here, so they canceled out. But sometimes
Yes.
if it was like a Z plus X times the cosine, would the X be the only thing that survived, or what would happen to that? Because
So are you saying say we had like a Z plus X hat term?
Yeah.
And it was dot DZ, like DZ Z hat or something like that?
Yeah, they're basically the same thing we're doing, but instead of just Z cosine, it's Z plus X times the cosine, like terms like that. What happened to that? Like, because I get a little confused with that. It just depends what direction it is, but sometimes I can't.
Yeah. So what happens is, right, is this is the cosine, right? So the dot product is just cosine, right? And so if they're in the same direction or opposite directions, right, it's 1 or -1. And since Z hat and Z hat are in the same direction, right, it's the cosine of 0 is 1. So they're in the same direction, so that means they're pointing up, right? So this is Z hat direction. And since we have a plus X, so we do X dot Z, right? So they're 90 degrees apart, right? So cosine of 90 is 0. So the X term just goes away, and you're left with just Z hats. And the Z hats will cancel, and you're just left with whatever you have, DZ or DS in this case.
Since dot product is A times B times cosine, the angle in between.
Yep.
Okay.
Okay. Next, what we'll do is we have to determine the self-inductance of the coil. And back when we were doing this, we had no idea what the heck we were supposed to do for this. So here's how you do the self-inductance for the coil. So, I mean, you guys did a lab with this. I don't remember ever seeing this when we did it in the lab. So we have, I believe, the flux. Is what this is called? Is equivalent to the B.ds. So we're trying to figure out. I'll preface this. You might think, okay, what's happening with inside the loop, right? So you think, okay, so there's H coming here, there are some B here, some B here, some B here. What we do is we assume that at the very center of the coil, all the magnetic field is concentrated, right? So we're trying to figure out what the maximum B is, and so that's what allows us to determine the self-inductance. Yeah, there's some other stuff, right out here, trailing out here, but as it gets closer and closer to the edge, it's really, really small. So we're really concerned just about the center. So what we do is, I think for this, the self-inductance, we can just easily do this right here. Oh yeah, ds. Yeah, exactly right. Okay, b equivalent to b. Okay, so this we know ds, right? So that's just the radius. So we'll just do r squared. I think we can do a squared here. I think that will work out. Okay. I think this will work out. I'll check it after we're done. Okay, this will be equivalent to mu naught I. So what we're doing is we're solving for the B field. I think we're using the relationship. I think we're using, what is it? There was something in chapter 5 where it talked about finding the B field at any location, or the E field. Mu naught I, alpha or just radius, pi over 2. Then what we got, I'll check this for you guys, sorry. L equals, okay, so then we have the, I believe this is capital lambda. Well, basically all it is it's just n times I, so, or n times phi. N times phi. I wish I understood more about this. I don't, it was just a lot of derivation when he was explaining this to us.
Real quick, Nick, in
Yes.
that term with mu naught at the end, is that a pi there?
Yes, it is a pi. Yes, sorry, it is a pi.
Why did the pi squared go away, and where did exactly the pi squared come from? The same equation where we got the 2 pi rn. Because you said that's wasn't that the dl or whatever or something, or the,
yes,
the ds.
Yes, but I think we're doing ds in this case. Let me just check real quickly. Yes, is this what we're supposed to do? Exactly. Okay, I'll go through the full steps with you guys here. So what we have for the magnetic flux is this right here. I'll write out what actually B is supposed to be. So we have Z hat. I believe this is for a loop, just any loop. I think you can find this in the book. I don't know what equation this is in the book. I will let you know. I'll look through it over 2r, excuse me, or just radius. Z hat, dA or ds. I'll just do it dA for you guys. From this, then we can evaluate this integral. We're going to get the same thing. Mu naught I pi r squared over 2r. And then we get this right here, mu naught I pi r over 2. Okay? And let me be more specific about this. This is actually wrong word I wrote down right here. Instead, what we have is the self-inductance, L, is equivalent to the number of turns times magnetic flux over your current. Obviously, this is just rewriting capital lambda, but just you don't have to think about capital lambda. You can just think about it in terms of n. What we can do then is we can just rewrite it. L is equal to n mu naught I pi r over 2. And then this is times I. Okay, we then have i's that cancel. And that's all that's left. Then we're left with this right here. N mu naught I, pi r over 2. Plugging this value in with all the values we're given. You guys need me to show you the values, or you have this exam?
We get the values.
Okay.
The result.
Let's see here. I'll just write this quickly down. Oh, sorry, this is the wrong one. Sorry. Okay, so for this particular problem, we have self-inductance is equal to 4.9348 e to the minus 6 henries. So we have this is 5 right here, 4 pi, 10 to the minus 7. And we have this right here. This is the total radius, so this is 0.5. And then 2. pretty small self-inductance, kind of flimsy. But this is helpful because what we're now going to figure out is what the actual like current that's going through this entire capacitor resistor series combination. So what we'll do is we'll look back at this again. We then now have the capacitors medium characteristics. So what we'll look at is we'll see that the dielectric is for E naught mu, so it's not magnetic at all, or it is, but just small. And then we have some conductivity. So because of this conductivity right here, we have to consider the displacement current as well as now the conduction current. So the conduction current, that's just basically an equivalent equivalent parallel resistor with the capacitor. And then we'll get the areas of the capacitors right here, 0.01 meters squared, and then separated by the plates, separated by like 5 millimeters. I'll draw the equivalent circuit down below so that we can get a better idea of what we're looking at. So we have our loops right here, and then we have some breakout points. You know, obviously this right here, very small, basically no distance between them. We'll have this resistor right here, so that's a resistor that's given to us. And then now I'm drawing like the equivalent circuit that I described to you. So we have the conduction equivalently, and then we have the actual capacitance. Okay. What we can then do is we can then write down what how to solve for the capacitance. Epsilon A over D, so this is the distance between the plates. This is epsilon, so this is just basically 4 epsilon naught. Area told us, I think this was 0.01 meters squared. We then find out that the capacitance, I believe, is C equals 70.832 picofarads.
What's the so for those values, what are all those values? Because the distance and all that stuff, like, can you write down the step in between that?
Oh yeah, sure. So this is 0.005, and then what we'll do is we'll just figure this out. So it's going to be 4. Let me just write this over to the side. So we have 4 times 8.8. What is it? 54, I think, times 10 to the, what is it?
-12, I think.
-12. Okay, I was thinking 21 for some reason. Okay, thank you. And then we have the area, which is 0.01 meters squared, and then we have the the distance between the plates is 0.5. Then when you compute this, you'll get, okay, so obviously this is times 10 to the -3. That'll sort of cancel out. Then you have times 10 to the -9, and then you have 4 times this, so that's 32-ish. You have, do you want me? I can work it out right now if you want me to, but.
Oh, it's fine. I just wanted to see that step right there.
Okay.
Nothing happens with the meter squared. That just stays 0.01, right?
Yeah, 0.01. It'll cancel out somewhere in the units. Yeah. Okay. That's it. That's, if you plug in those values, that's what you get. Just checked it right there. Okay. Now what we have is, after solving for the capacitance, we then have to solve for the resistance. So remember the equation for the resistance. It gives it to you as conductance first, but of course it's just 1 over conductance. So R equivalent is then L over sigma area. L is of course the distance, I believe. It's the same thing as D. So I can just rewrite this as D over sigma A. We're given sigma, I believe, as 2.4. Is it right? 2.5. So we can just do 0.005 over 2.5 times 0.01, and that should give you 2.2 ohms. So it equals 0.2 ohms. Yeah. Okay.
Yeah, that's right.
Okay. After this, we can then solve for the equivalent, not the equivalent, the equivalent impedance right here for this guy, so that we can just combine them together as one unified element, so that we don't have to worry about finding out the current here or there. We can just do that using our favorite methods of just multiplying the resistance. So you do Req over J omega L, excuse me, J omega C, and then you have Req plus 1 over J omega C. Okay. Then what we'll do is we'll add the 5 ohm resistance that's given in the problem. So it tells you this is right here 5 ohms. Just part of the loop, or not part of the loop, just part of the connection in to the loop. So this is plus 5 ohms. We then find out that the impedance is equivalent to 5.2 minus 1.06812 e minus 9I. And this is all ohms, of course. Okay, so now that we figured out the resistance, basically the impedance, we're given the VMEF, right? Or from the VMEF, we can find the loop current. We can find the voltage, of course, as well. All that we have to do is it's basically we go back to our transmission line problems. We just say average power in R is just, I'll just write this down, PR equals the real part of VR. So this is EJ omega T. So this is actually a phasors times I loop conjugate. And what you can do right here is you can, what I did actually, was I replaced VR with just R times I loop. Let me replace this right here. Real, excuse me, R times I loop times I loop star conjugate. So this is just looking at purely the resistance right here. This is not overall resistance. I was just only solving this, guys, just for figuring out how to solve for REQ and capacitance. I think you had a problem on your homework that asked for that, just to go over it. And what I got was 202.635 kilowatts. Does that make sense?
Nick, I just want to clarify the resistance we use in this calculation. That was the like equivalent impedance we just got.
No, that is sorry. I believe this is actually just the 5 ohm resistance. Time average power dissipated in the resistor.
Okay.
Okay, where did the current come from?
The current, this is just the current from the loop. So what you do, once you solve for, actually, I guess this is why we have to solve for it. Once you solve for the total impedance, you can then do V equals IR, right? And so you have R, right? And you have V. This is your VMEF. So you have VEMF over R equals I. And so all I did was you just find the I, I just plugged it in here and here. And the R that we're using is just the 5 ohms, so I just plugged it in there.
Okay. Thank you.
Do you guys have any questions on this problem with the loop problems? I know this was kind of wishy-washy, or the way I was going through it was kind of weird. The problem that we had on our final exam for this wasn't that bad. I think it was pretty good. If you want me to, I can maybe go over something from there, but after Easton is done or when we have time. Any more questions?
Not on this one. This one's okay.
Okay. Sorry, I guess I'll move this stuff over for Easton. Let's see here. Okay, Easton, I think you are up.
Do you want to keep sharing your screen, or do you want me to share mine?
I can. Are you going to do problem 2?
Yeah.
Yeah, I'll just share your screen. I'll just keep this screen up right here. I can see what you're
Okay.
writing.
Okay, so starting off with this one, you're given the electric field, like a general form for it, and it's asking for the magnetic field intensity, or not the general form, but you're giving the actual electric field intensity, and it's asking for the magnetic field intensity. So I'm actually going to use Faraday's law, which is the same thing that Nick just used, but he was using the integral form. The integral form is like, let's see, I think it's
Yes, it was the integral form. Yep.
yeah, integral of I think it's over close contour of dl. Oh my god, dl, and then that equals over a closed surface. Oh wait, no, excuse me. It's the derivative. So, my goodness, I don't know how to use my new writing pad. Bear with me. Okay, negative. Okay, yeah, so it is over a closed surface, but it's the you're looking at the, so y'all know Faraday's law, right? You're looking at EMF, it's the changing flux captured by the loop is gonna induce a voltage around the loop, and that's kind of what the integral form is saying. I'm really having trouble writing it out for some reason, so I'm just gonna go on to the differential form. So Dr. Twatch has probably briefly mentioned how there's an integral and a differential form. The reason we go with phasors a lot is because they're just easier to work with. So for like the integral form of Faraday's law, it's better for finding like the actual EMF, if you're asked for that, or like the current, like specific values like that. But the differential form is really useful for just giving like a relationship between magnetic and electric fields. So using the differential form is a lot better in this case, since we're just given one field and trying to find the other, which is going to be del cross E, and again, we're working with phasors now, equals derivative with respect to time of B. And then an important relationship y'all need to know, there's one for the electric field and the magnetic field that relates the field intensity to the, so yeah, for magnetic field, it's B equals magnetic permeability times H. So that relates the magnetic field intensity with the, oh my God, what is this called?
Magnetic flux.
Yeah, magnetic flux. So as you can see, this is like, I mean, you're pretty much given E, and then you have to do a cross product, and then you'll pretty much just have B on the other side. So this can kind of be written with, Dr. Twacha derived this for y'all in class, but since this is a derivative with respect to time, you can kind of think about like the general form we've been using. And then in phasor, it would be but when you're taking the real part, you have the e to the j omega t in there, so you can kind of think about if you were to take the derivative with respect to time of b, you would actually get, and then you still have to sub in this as well, but this right side of the equal sign would become j. Excuse me, sorry, I'm skipping this. Negative j. And then this mu comes from, because we had to sub in b and h, and the j omega comes from taking the derivative with respect to time. And then you still just have h on this side. And so since we're solving
I think we
You
lost
might,
Jason. So yes, I'll just kind of fill in the time. So what we've basically done right here is we've done 1 over j omega, j omega, and that's basically the Fourier equivalent of ddt. And I don't know why the omega is still on top. Sorry, it's probably actually supposed to be on top. 1 over j is basically the j omega should just be the
it's supposed to
equivalent.
be on the bottom.
Sorry, I was just filling in the blank. Sorry.
Can y'all hear me now?
Yes, we can.
Yeah, we can hear you now.
I don't know what happened. Yeah, so then since we're solving for h, and sorry, my notation's all messed up. This is, oh my gosh, I'm not even on looking at. Yeah, this is phasors when you're in differential form. Don't forget that. Dr. Twacha will be pissed. So then since we're solving for e or h, moving this stuff to the other side, dividing by negative j just gives you positive j. And then you have the over omega mu naught, and then that equals h. So that makes this really easy to find. You're literally just taking the e that you're given above and splitting it up. So let's go ahead and set up so this is equal to j omega. Nick was writing better than me with a mouse, holy shit. And then cross product. So dx, dy, dz. And then you have to split up e in terms of its x and y components. I'm sure y'all are capable of that. So for x, it's going to be negative j377 e to the negative j2 pi z. And then for y, I'm going to kind of write, and then that has an x hat. Oops, motherfucker. X hat. And then for y, you're just taking the y component, and it has no j, so it's just 377. E to the negative j2 pi z, and then the z component 0. And so...
Does the y not get a y hat at all?
Oh, yeah, sorry. It's kind of, you can leave it out and you'll get the same answer, but it's better for notation. I'm just going to write with my mouse. This writing pad's doing me no justice. Hello?
Yeah, we can hear you.
No, it's not let me write.
Oh.
Sheesh.
Writing pad is supposed to help with technical difficulties. Okay, but anyways, y'all remember how to take cross products?
Somewhat. I wouldn't mind going over it real quick.
Okay, so when you're getting the x component of the result, oops, turn my pen over. Okay, so we're still gonna have this j, go u naught out here. And so when you're getting when you want the x component of the cross product, you cover up the like all the x components. So like you would cover these up and just look at the y and the z. So you would take dy times 0 and then you're going to subtract. So you're taking the like top left, and it's kind of hard to. Okay, you'll just see what I'm doing. So you're covering up all the x components when you're getting the x1, and you're taking the like left diagonal, so dy times 0, and then you're going to subtract like the right diagonal. So
you're just multiplying by the determinant of what you have left, right?
yeah, the term. Dz times negative j377e negative j2 pi z, and so that's just the x component of your cross product. So then you do the same.
Why do you have it as negative j? Isn't negative j the x term? You're supposed to not have the negative j for the 377 e. The dy wasn't it?
Yeah, sorry, I making so many mistakes. Jesus. Yeah, so z times, yeah, the one in the middle. You're right. Sorry, I should have wrote that better. Yeah, so then you're going to cover up the y column. So for the y, you have dx times 0, and then minus, now I'm actually going to use that one, dz times negative j377 e to the negative j2 pi z, and that's your y component. And then for your z component, you cover up the 0. So you have, oh wait, and also when you're doing the y component, it's the sign is flipped. So put a
You kind of cut out there a little bit, Eason. You said when you're doing the Y, the sign is flipped, and then I didn't hear anything after that.
I don't know the derivation for that, but I just know you have to have the negative sign there, or your answer is wrong.
Okay.
That's
Fine.
that's calculus through stuff. I remember why I can't explain.
And then so yeah, z component, z column, make sure I actually multiply the right terms. Dx times 377 j2 z, and then you're doing minus a negative, so it's just plus d y. That's your z hat. And the z hat, you can actually see it just goes ahead and cancels out because derivative with respect to x of this is 0 and derivative with respect to y of that is 0. So you only have the x and y components down.
Are you speaking? Because we can't hear you.
I don't see him writing either. He might have disconnected again.
Okay. Shouldn't there, that J omega mu, shouldn't that apply to each one?
I haven't can you hear me?
Yeah, we can hear
Yeah,
you.
we
No,
can hear you
no,
now.
no, that J
It gets
yeah,
distributed to all those terms. I just don't have I need to put a big bracket there. Because this is the whole cross product that we just did right here. Y'all can still hear me, right?
Yes.
Okay. I don't know why my mic's cutting out. Okay. So derivative with respect to z of that top term is just, oh, and also it's probably easier to just go ahead and factor out the 377 e to the negative j 2 pi z because it's common between everything. So I'm going to do that right now. Just less stuff to keep writing. E to the, or actually, so so derivative with respect to z of e to the negative j 2 pi z is just negative j 2 pi. So then you're left with negative j 2 pi times e to the negative j 2 for the top. And that's becomes positive because of this negative sign. And then for the y term, remember we have this negative sign, so bring that over here. Derivative with respect to z of this is the same thing, but with a j. So j times j, oh my gosh, there's a lot of negative sign stuff going on here. So it's going to be negative j times negative j, which becomes still negative 1. And then you already have a negative sign there, so it becomes plus. Plus. And then that's going to be, there's no j there because they canceled out. So it's just e, or excuse me. Two pi e negative j 2 pi z. Oh, and this is x hat. This is y hat. Okay. So that was a lot of mistakes, but we made it to the right answer that I have at my disposal. So then you can further factor out this e to the j 2 pi z if you really want to. It'll make your job easier in a second because we have to use this again. So I'm going to do that. So j377 make up u times 2 pi e to the negative j 2 pi z. And this is times. So once you factor out, you're just left with j x hat and then 1 y hat. And that is your h of z. Sheesh. Okay, so then you're also going to use that, or wait, what's the next part?
Can I also say something too as well?
Yeah, sorry.
Okay, so I guess one thing, Easton did this, I think, correctly, from what my answer seems. Yeah, I think he did this correctly. He hasn't gotten to the next part yet, but what you can do right here is, maybe you guys have seen some of the homework already, but if you recognize that 377 is approximately, I think it's just called the characteristic, or what is this called? I forget what this is.
The
intrinsic impedance. Yeah, exactly. The intrinsic impedance. All this is basically just a relationship between E and H, right? What you could have recognized is it's approximately equal to this, which is approximately equal to 120 pi. Not a lot of these are good approximations. This one's probably the best approximation, but if you recognize this, you could have used this, and you would have gotten this equation right here. Not E hat, E. Not that one, actually, excuse me. These are both wrong. These are time. And then all you would have recognized is that K is the direction your wave is propagating. So in this case, it's Z hat because of this right here. It says minus 2J pi Z. It's in the Z hat direction. So all you got to do is just compute two simple cross products. So you just got to do Z hat cross minus X hat, and that gives you minus Y hat. And then you do Z cross Y hat, and that gives you X minus X hat. And because you set this is minus or as 377, you can just divide by 377 and you got a very simple answer quickly too. But I mean, there's both ways you can do it. Sorry, I just wanted to show them
No, that was good.
the other route.
Yeah,
I
'cause,
think
I mean,
remember
that's an
seeing on
important
the homework.
concept of this class too, is that like Dr. Twacha gets mad as hell at us because like when we do these reviews and stuff, he sees like people go into the test and copy like what we're doing step for step, and like even when that's not the right like thing to be doing, and like he knows that y'all are doing it too because there's so many ways to approach a lot of these problems. But like it's hard to like give a review for the test for y'all that's like beneficial, and it's like not just like another lecture, because like lectures are really easy to just go over your head like we but yeah, also it's kind of like a double-edged sword doing the whole just solve problems for y'all. But anyways, moving on. Do y'all know the difference between propagation and polarization?
No.
No.
Okay, so like if this is the wave and this is the Z direction, then you say it's propagating in the Z direction. It's just like the direction it's traveling, but the direction it's like moving up and down is the polarization direction. So like if we were to look at this wave straight on, it would just look like a line, but there's also like waves that look like circles and waves that look like ellipses in the way that they move on the third axis. So most of the waves you guys have been working with up until this point have just been linearly polarized, and you can tell because there's usually just like a like X hat or something in front of like the general form of the equation. But this one, let's see, what is E?
I guess also one thing to ask too is this a plane wave? Does this satisfy the conditions for a plane wave? And yes, because the amplitude is constant, and the direction, even though it goes in only one direction, it's because the amplitude is constant.
And do y'all
throughout the
know
entire
like
space.
where he derived the because I remember not understanding at all the derivation for the general form of the plane wave equation that we use, but all it is he decouples the Maxwell equations so he can get a relationship between like he can look at E and H independently, and then he just like solves it like a differential equation and gets a general form of the equation that fits it, and that's the general form that we've been using for all these waves. But anyways, so propagation and polarization. The part B is asking for the polarization of the wave, and so E of X is given as what? Okay, five. Oh my gosh, can't speak either. The writing pad has me fighting for my life. Okay, E of Z is given as 377. Squinting. Is that negative J X hat? Negative
Yes,
J
it's
X hat
negative J X hat plus 1.
Negative J X plus Y. And then it was just E to the J 2 pi Z. You can tell this one isn't linearly polarized because it has two like degrees of freedom, and this is where the polarization vector will be. So if you go to your book, this is the easiest way I can think of to explain this, because it like Dr. Tawacha derives like this angle and stuff, and the book kind of talks about the what is the name for it? Just go to 348 in your book. Yeah, it defines the inclination angle, and you're supposed to find like if it's positive or negative to see like if the like which direction the circle is moving. So, I mean, also it's circularly polarized because the magnitude of the x and y hat vectors are the same. I recommend that you just read the brief section of the book over polarization. It's not very long, but the conclusion they come to, if and it's defined in terms of the x-axis. But the conclusion they can come to is that if x and y hat are of the same magnitude, and there's only a phase difference, then it's going to be circularly polarized. And then all you have to do is find out if it's left hand or right hand circularly polarized. So the book says when, I think it says when y is 90 degrees behind. And so, hold on. Also, I should do this. Are y'all familiar with this? How that works? Just going between the value of j and like a phasor.
I'm kind of familiar with it. I've used it before.
Yeah, it's just, this is just saying that j is equivalent to a phase shift of 90 degrees. So if you look at, and then negative j would be, negative 90 degrees. So if you look at negative j x hat plus y hat, it's telling you that x is 90 degrees behind y, which you can also say y is leading x by 90 degrees. And in the book, when y is the one leading by 90 degrees, then that is left hand circularly polarized. So this is LHC polarization. And you can just, to satisfy Dr. Tawacha, write out like an assumption, like y leads x by 90 degrees or something like that. And that's really all you have to do for part B. That's all it's asking.
Okay. So for this one, if I'm getting this right, so the x hat, the negative j, so it's shifted 9 degrees behind. So y is above, so it's y's primary. Why does that make it left hand shifted? Again,
if you look in the book, it'll derive the inclination angle, and for that case where y is leading by 90 degrees, it says the inclination angle is -0, and so left hand circular, like the left and right hand rule, like left hand, like if you use your left hand, have the thumb pointing out of the page, and then your fingers are curling like in the direction it's traveling. So if the inclination angle is negative, that means it's going clockwise around the unit circle. So that's why it's left hand circularly polarized, because if you put your left hand on the axis, that's the direction your fingers curl to follow the inclination angle. But like it's not really necessary to do that derivation, since you can just kind of look at it and see if x is leading y or y is leading x, and he's only going to give you differences of 90 degrees probably.
Easton, do you mind if I show him how I would have approached this? I'm not saying your approach is wrong. So
because I honestly like didn't understand how to get the inclination angle, because the j is attached to the x.
I don't get the inclination angle. So this was like we were working in like a group at the very end, and what we came up with was the following. So we actually took E in terms of its in its time representation too as well. So we got the following x hat 377 cos, and then we had omega t minus 2 pi z minus pi over 2, and then we had minus y hat 377 cos of omega t, right? Yes. Minus 2 pi z. What we then did is, this is how Tawacha kind of explain it, right? So like imagine you're looking at a cell phone tower, and you say you plant yourself in like one particular position, and at this position you say that is where your wave is coming towards you. So then what we do is that, so that basically means that at this point right here, z is equal to 0, right? We don't care about what's going on behind us or what's going on in front of us. It's what's happening where we are. So if we set z equal to 0, we can simplify this a little bit more. And so what we're doing now is we're just observing what's happened directly in front of us or directly at us. So we'll say 0 right here, and then we'll say t. This gives us 377. I believe this is sine. Yeah, sine omega t. And then this is minus y hat 377 cos of omega t. Okay, and then what we can do is we can think about this now in terms of like a graph. Obviously, this is like, you know, where the book kind of goes to as well. They think about it in terms of a graph. Let's say that this is our x hat direction. So then using our right-hand rule, this has to be y hat. And because z is coming at us, it has to be like z hat this way. So z hat this way. So the wave is coming this direction. Okay. Then what we'll do is we can actually kind of manipulate this in a way that'll help us out. We can set a time. So let's say a time that is equal to pi over 2 omega, right? So that'll cancel out the omega, so we don't have to worry about it. And we're just left with pi over 2, right? So then what we get is we get, if we plug pi over 2 omega, we then just get 377. This is 0. I think this then becomes 1, so this is just 377. So it's in the positive x hat direction, right? Positive x hat direction. Right. Yes, positive x hat direction. Yes, so positive x hat direction. So that means it's right here at pi over 2, so t equals 0. It's going this direction, so it starts right here. And then when we say we just do pi, right? So we just do pi over omega, right? So then we do e 0, let's say pi over omega. We can then say this is equivalent to, well, we plug in a pi, that's just 0 right here, and that turns it into -1, then it's a positive y hat there. This is equal to, so we have -1 right here, but it cancels out because of that minus, so it's just positive, so then it's y hat 377. And so then what we do is we then go forward, we figure out, okay, this is in the y hat direction. Let me think here, actually. I'm trying to think about this correctly. Okay, sorry. This basically what's happening is, I think at this point right here is what we have. I'm trying to get this right for you guys. We have a y hat direction right there. Okay, so let me back up. Sorry. This method works. It's just I haven't used it in a while. Let's say that now time equals 0, right? Let's just say that t equals 0. What we can do now is we can just say that it turns into. Oh, I think I see what I did wrong here. I see what I did wrong here. There we go. Okay, I accidentally had a minus. It should be a plus. If we have a plus, let's just keep it as this. So then we'll just set time equal to 0, 0 comma 0. This cancels out because that's just 0. So then we have a positive y hat. Y hats. Then we have 377. That makes sense. Okay. This is at time equals 0. This is then at time equals, what is it, pi over 2 omega. And you draw a line that goes from here to here. You see that you have to use your left hand to curve in that direction. And it just all works out. That's how you determine it's left hand circularly polarized. I know the way I described it was so bad, but this worked for me on my exam. And I think this method may make a little bit more sense because I was trying to look at the book and inclination angle just comes out of nowhere.
Yeah, they don't really even like explain it. They're just like, this is inclination angle, and here's the derivation for it. It's like, okay, but what is it?
I hope I haven't confused you guys. Sorry. I know I was being a little confused there. Sorry.
No, that makes sense. I mean, you're
No, I
basically
saw
just
that.
you're plotting it out, right?
Yeah, just plotting it out.
Okay, then part C is it's plug and chug. Basically, you just get to do another fun what's it called? Cross product. It's asking for what is that called again? The average power density. Oh, it's also asking for frequency. We could have got frequency way earlier, so we could have simplified the magnetic field intensity, but you already have beta, because like it's just given in the vector form of the electric field intensity. It's just 2 pi. And do y'all know how I got that?
Not quite, but I'm kind of familiar with. I mean,
So if you look at to the left on part B where I wrote out the phasor form of the electric field intensity, do y'all remember converting from phasor to time domain or time varying, excuse me? So you take the phasor part, multiply by e to the j omega t, and take the real part. So that you end up with cosine omega t plus, or excuse me, oh my gosh, minus beta z. So you're given the phasor form, e to the z, so you can just go to this time varying form and like you're putting the e to the j omega t in there and then taking the real part. That's where the omega t comes from. But the angle that's already in the phasor form, that's your negative beta z. Do y'all remember that?
yeah.
Okay. So yeah, and then it's positive because it's propagating in the positive z direction, so that means negative z. I'll go over that a little bit for problem 3. But yeah, so beta equals 2 pi, and then you have some relationships for beta. One of them being equals omega root magnetic permeability plus electric permeability, and you have these two values. I believe they're given in the problem statement. They are, because it's just free space in free space, so it's mu naught and e naught. And then we know omega equals 2 pi f. This is all trying to solve for frequency, in case that became unclear somewhere in the process. So yeah, we have 2 pi, we can divide 2 pi over, so then this just becomes 1 over mu naught equals f. And so you can just plug and chug that to get f. I don't actually know if I plugged that in my paper.
Well, it turns out that 1 over mu naught epsilon naught is just
Is that
c.
just an equation?
That's just c.
Oh.
Yeah, that's just speed of light. No need to plug it in.
Nice. Okay, so yeah. Anyways, frequency ends up being speed of light. He does that a lot in these problems just to simplify stuff. Like when you're trying to find beta or propagation speed, you'll notice that like, oh, beta just equals 2 pi or wavelength is just 1. It just makes the math a little easier because these questions are often scary enough. So yeah, that's how you get frequency. That's the first part of problem C, and you can also use it to simplify the magnetic field intensity if you really wanted to get him giddy and happy. But for the second part of problem C, he's just asking for the power of the wave. Oh my gosh, my whiteboard. Yeah, so he's asking for the average power density of the wave, which is given by phasors again, because they're easy and fun. The real part. yeah, so like I said, no funny business here. Oops, I should be bracket. It's just a plug and chug. You have this, and you basically have this, except you're using the complex conjugate of the magnetic field intensity. Y'all know how to do complex conjugate, please?
Yeah, it's kind of like an inverse of like a fraction or something like that. Okay,
Yeah.
there's also a thing on the calculator for conjugate.
But I mean, basically, you're just making the you just make the angle. You just flip the sign on the angle in the phasor form, and you'll be good to go. So I'm gonna set this up, but as you guys saw from my fun algebra mistakes earlier, I'm gonna let y'all run through this cross product now that y'all have seen how to do it, and then I'm gonna give you the right answer so you can check your work, obviously. So simplify a little bit more. What half? Woo, cross product. Okay, so when you're doing the cross product, you also have to remember that like the first one in the cross product, the one on the left of the sign, so in this case E of Z, that goes on top when you're writing out like this big block for your cross product. You have to remember that the one on the left goes on top and that when you're doing the y hat value, you put a negative sign or your cross product is going to be wrong. So for e to the z, splitting it up into the x and y z terms, get negative J377 J2 Z 3. And then the z component is 0. Here. Those are my columns. And then for magnetic intensity, negative 77. Yeah, 2 pi. And then the angle like is negative in the answer for that we got for h of z. So here it's going to be positive because it's complex conjugate. So you just flip the sign on the angle of the phasor. So we have e to the plus j2 pi z 377j. Oh, there's that 2 pi. Again, positive, and then 0 for the z component. And then you do your fun cross product stuff, you know, where you cancel out x row. And then, so yeah, you'll end up, we can kind of go through it here. So you can see that for the x component, it's just going to be 0 because when you cross out, when you cross out the x column and do the diagonal multiplying, you just get 0 for both terms, and the same thing for the 1 here. And then the z term, okay, so if you can see, like, if you were to multiply this term and this term, you see what would happen to the j's? Because, like, you know, when you are multiplying exponents, you add the power, but since they have the same argument, one's positive and one negative, it just cancels out pretty much.
It's kind of hard to hear you, Easton. Sorry.
Yeah, I kind of have a inkling of what you said.
Is it like volume?
No, it's like cutting out.
Goodness.
But what I think you said is that when we're multiplying and those e's are gonna cancel out.
Is it still cutting out?
Not right now, no.
Okay. I haven't been having problems with my mic. I'm sorry about that, guys. So yeah, when you're like multiplying those two underlined terms, the e to the negative j 2 pi z and e to the j 2 pi z, like when you're multiplying exponents, you just add like the power. So when you add those up, they cancel out and the e's go away. So then since you're taking the real component, like all your j's end up going away because you'll see the only two terms with j also multiply by each other, and the j cancels out. So you just end up with, for the z component, hope y'all can still hear me, I'm sorry. E77 squared over. It's supposed to be a pi. So you actually just get two of the same term. And then so you're going to take the real part of this, which, oh, sorry. So yeah. Which the real part is the whole thing because it's all real. And then you do 1/2. So you're basically just taking one of these terms because, I mean, there's two of them. So for S average, I think you should end up with 377 squared over u omega 2 pi. And that's your power. And then I'm sure he wants you to plug in for omega's 2 pi f, and that's given. Okay, so problem 3 is like basically just applying concepts you've had to know for problem 1 and 2. Can you also hear me?
Yeah.
Problem 3 is basically to give me. Are you zoomed in on it? Okay. So it's just asking you to write the wave equation. Yeah. So it's asking you to write the time varying vector field intensity given all of these like properties. So I have some givens. F equals 10 times 10 to the 9. Given E. So basically you can just kind of start with the general form of the equation and just like see which values you need, which is just this. Should this by now. And it's not the vector form, the time form. So it's a function of z and t, and that's just gonna for like, okay, so remember I was mentioning this propagation, or not, excuse me, polarization vector, where it's linearly polarized. This is just the direction it's polarized. You can see it says it's polarized along the x direction, which means linearly polarized. So it just means the whole, like, the way that the cosine is oscillating is only in the x direction. So yeah, that's why it's attached in front of the cosine. But this is, I'm still just writing out the general equation. So that's the general form just for a wave propagating in the positive z direction and polarized in the x direction. So Dr. Pacha probably briefly went over this with you guys, just all the times we've been looking at the general form with, you know, minus k, or k is the beta, sorry, switch my notation. With the minus beta z, that just means it's propagating in the positive z direction. That's just kind of something you have to remember. So, and then also it's really easy to remember polarization direction. So right off the bat, just by reading the problem, pretty much you have two of the values. So we can kind of start with the actual values. It also gives you the peak value, the electric field intensity when z and t are both 0. So if you plugged in well, you already know peak value as 10 is going to have to be attached to the front of the cosine. It's like peak magnitude, basically. Then you have to solve for beta using some relationships from earlier. Right. Oh wait. Okay. So you can the propagation speed, which is just the speed of light. ER, which is just the speed of light.
I'm sorry. Is anyone else having a hard time following what Brian is saying?
I guess it is.
Yeah.
It is kind of difficult to hear you. Brian, sorry.
Yeah, it's a
Houston.
little hard.
Do you want to explain this one, Nick? Then am I still cutting out?
Yeah, it's like the volume is like rising and it's like a cosine of
Do you want to
volume.
explain this one? It's not very
it's
clear. Sorry.
I guess I'll just kind of repeat what Easton said. So what we're starting with is the general equation for a plane wave. So we have the amplitude, the frequency, the k vector or just beta, free space constant, and you have the phase offset. So what we can do is we can first look at finding what k is. So to solve for k, all we got to do is just recognize the following. So we have k is equivalent to beta. We're not really given anything about it, I believe, correct? Yeah. I think all we're just told is that it's equal to mu naught, or excuse me, omega square root of mu epsilon. I think so. Is that what it did? Yeah, I think. Okay. Oh, okay. I see. Yes, the speed of the wave propagation, exactly. Okay, then from here, what we can do is we can recognize that this is just 2 pi times f, which is just 10 gigahertz, times the square root of, it's just basically just times 1 over c. Actually, no, not really. Let me replace this statement for real quickly. Because we're given the actual medium characteristics, what we have is we have the square root of mu naught, which is, lucky for us, there's no real change there. But then we have epsilon, so we have 81 epsilon naught. Okay, and we're given what epsilon is, luckily for us. Then what we do here is we can kind of take some of these terms out. So the square root of 81, 9. So we can just take out a 9. And then we have the square root of mu naught epsilon naught. That's just 1 over c, or this not the speed of light, but it's just the movement, or just 1 over c, just the value. Then we have 2 pi times 10 to the 10 to the 9 right there, 10 gigahertz. And then we're dividing this by c, and then it's multiplied by 9. Sorry, this is so messy. Let me rewrite this. 2 pi times 10 to the times 10 to the 9, 10 gigahertz. Then we have mu naught, so this is just 1 over c. And then we have times 9 right here because we took the square root of 81, which is just 9. We can solve for this, and then we get beta is equivalent to, or k, 1.886 kiloradians, or just E3 radians per meter, I think. Yeah, per meter. Okay, we can plug that value in for k right up here. We'll just write equal to k. We can just plug that in right there. Okay, then the next thing is, okay, the phase offset. What we have to realize here is we can just plug in a z. So if we're told z equals 0, okay, so then we can kind of cancel out this term. So I'll erase all this later. Okay, and then we say t equals 0. And we're told that the maximum, which is a, occurs when z equals 0 and t equals 0, which means that the phase offset is nothing. So what we can do is we can just say that we can just cancel out this term, and we're just left with this right here. So we don't really need this term. This is just 0 degrees or 0 radians. Okay. And now we can write the entire form out as we can kind of replace our terms that we put in right here. He was starting to write it out right here, so I'll just write it down at the bottom. So we have the electric field, ZT. We then have this is equivalent to x hat 10 cosine. And then what maybe you might be able to get away with writing omega t if you say what omega is. I'll just write it down. 20 pi times 10 to the 9 t. You just take this term right here. And then we have this right here, which is just plus 1.886 E3. And then we have times z. And we have plus 0. You can put a plus 0 out here for completeness if you want. And this right here is in your volts per meter.
Should it be minus?
Oh, it should be minus, exactly.
Wait, that's not okay. Wait. It's okay. So, isn't it minus and positive z direction, and this one wants the propagation to be negative z, so it wouldn't be plus?
Whoops, I didn't see the.
Oh, it is. It is. Okay. I guess it was copying mindlessly from my paper. I'm so sorry. So it is plus. So exactly, because it is in the minus z direction. Okay. And it's polarized along the x-axis, or x direction. Sorry. This is basically a simple give me problem. If you could write all of this down within like 5 minutes, you would get maybe a bonus. Like, I mean, think about how easy that would be.
And he's probably pretty likely to give like y'all a question like this.
Mm-hmm. Yeah, I mean, we got a question similar to this on our final exam. It was, it asked more like directly about like, okay, what's the polarization? It basically rewinded everything. Like, so he gave you the equation and you just had to like break everything down. So you had to tell him, okay, what was your propagation direction? And he asked for stuff like wavelength and frequency. So a little bit more involved than this one, but I mean, still pretty short. I think that's it, right, Easton? For all the questions that we're going to cover. Do you guys have any other questions more regarding on chapters?
No, I don't think I have any other questions.
Okay. There's the relationship between lambda and k. So, I guess one thing, maybe, I don't know if they'll throw this at you guys, but definitely be prepared. Like I was trying to be prepared as well on my exam. What we've given you, I guess, in the previous example right here was the in the free space when there is like no conduction, right? And for a lossless medium. So this right here is for lossless medium right here, which is, I mean, generally okay, right? But say he gives you like in a lossy medium, then what you do for a lossy medium is you have to consider the complex permittivity, I think, permeability. So epsilon c, which is the complex one, is your epsilon, right? Whatever you're given, and then it's minus j omega c, or excuse me, omega over, sorry, sigma over omega. So this is your conductivity of the medium. Then what you get, of course, is for the conversion between the E and the H, you get, I think for the, it stays the same for the, I guess for the magnetic field. It still remains 1 over j omega mu naught divergence of, or the cross, I think it's divergence, or the curl, sorry, the curl of E. But for when you're trying to go the other direction, when you're given the H, or say you're, given the H and you want to find the E, what you do in that case is you do 1 over J omega epsilon C, so your complex. I mean, the only reason it's complex is because it has a J in the term. It doesn't mean like it's hard or anything. It's just it's complex. And then, oh, let's see here. There you go. This is just delta, or excuse me, the curl of H E. Just your E field. Nothing else changes, right? So your lambda is still the same. 2 pi over K. Your omega is still the same. Your omega still remains the same way we did it last time. Or sorry, your K, your free space. Omega, mu epsilon. And then your propagation velocity still remains the same as well. 1 over square root of mu naught epsilon naught. There you go. I don't know if he's going to ask you guys anything about that, but I'd be very, very careful. And I guess I also want to preface something too. This right here, you can't just use. Well, let me see. This right here, you can't just use willy-nilly. You just have to. You first have to make sure that it's a TEM wave, so a transverse electromagnetic wave. And because plane waves are a part of the TEM wave family, this can be done. This can be used.
Can you go back to the equations you just wrote a second ago?
Yeah, sure. This is for lossless medium right here, or lossy medium. I mean, he might not give it to you. It might be a little bit more work, but I mean, it's not going to be that bad, right? If he gives it to you, because like say if you're given a lossy medium and he gives you the E, right, and you're just trying to find the H, nothing really changes. So, from the previous problem that we showed you.
Yeah. Small thing.
I guess one tip I would try to give you guys is like, I mean, we solved some problems and y'all can look at our steps and stuff, but Dr. Twatch is likely gonna, like, it'll be the same concept, like finding one field given another. He's just gonna switch up givens and what he's asking for a little bit. Just remember that the differential form is going to be a little bit easier for going in between types of waves, whereas the integral form is usually used for like finding something specific. Like Faraday's law, the application is usually like for finding inductance or EMF.
Yes, the integral, I think he's probably explained it to you guys this way. The integral is more realistic to us, right? Because you're summing the small little components to get to something that you can measure that for us. But the differential form is, like Easton described earlier, is to create a generalized relationship between two things, and when you're also at the boundaries between two mediums. And then I guess we should cover one more thing. Do you guys understand the difference between the displacement current and the conduction current, or the put-in current?
No, not personally.
Okay, so, or the impress current density. So obviously from the differential form of the equation, we have delta H, or excuse me, not delta H, sorry. We have this right here, which is the impress current density, or sorry, this actually is the impress, which includes the conduction current as well. Then we have our displacement current right here, which is ddt. Okay, this guy right here contains the current put in and the conduction current as well. So the current put in is your impress current. Not that you guys will have to recognize this like on the test. Just so that you guys have like an understanding of like what all these things mean So impulse current, he's probably described it to you as, imagine you're at an antenna, right, or you're broadcasting some signal, and the impress current is what you put into that antenna. So imagine it's what is a part of your transmission line. And then the conduction current is the conduction in the medium that your signal is going towards. And the displacement current, all that really is imagine you have a capacitor, right? Just say this capacitor right here, and you have some voltage source tied to it. Sinusoidal. It has to be sinusoidal, correct? Because there's no change in voltage. If there's no change in voltage, then there's no displacement current. That's because of I equals C dV dt. So no change in voltage, no displacement current, or no current through, no current. Of course, if there's some conduction, then there is a current, but whatever. That's conduction current. Displacement current, all that is, it's the appearance of charges suddenly moving to the other side. Right? So if you have, say in this phase, right, or this time frame, you have plus plus and you have minus minus. And then the next time frame, you have, say, minus minus on this side. And then you have plus plus right here. It appears as if the charges either went through this, but instead what they do is, because this right here changed from positive to negative, it reversed. So you went from this, you went from this state in the first stage, and then now what you're at, the stage you're at right now, is you're at this stage right here. The charges repel each other. The charges repel each other. So it's just the currents moving in this direction. They're going back and forth. They're not going through the capacitor at all. The current that goes through the capacitor is the conduction current, which is caused by the conduction of the medium. And so that's basically just the resistance. Displacement current only appears if you have a changing voltage, which is why I drew the sinusoidal source. If you have just like a battery, the best you're going to get is conduction current. Do you guys understand that?
I think so.
Okay. You guys have any more questions, or you guys just wanting to go and study on your own? Okay, well, I guess I can end the recording here. I can also, after this recording gets processed, I'll upload it to YouTube, and you can look at it again, check it out later. And tomorrow I have office hours from 11 to 12, and then Tuan also has his office hours from 12 to 1 as well, tomorrow, Monday. So you guys can come in and ask questions before your exam Tuesday.
All right. Thank you.
Okay, good luck, guys.
Thanks, Nick. Thanks, Easton. Also,
sorry about
congrats,
the mic,
Easton,
guys.
on getting approval from Dr. Wetz.
Oh my gosh, dude, my heart almost pounded. I saw him unmute his mic and I was like shitting, and then like it was completely flipped my expectations on their head. Sorry about the mic though, guys. I think it was because I have noise suppression on, and my teammate, or not my teammate, my roommate is a loud gamer.
A loud game. How funny. Okay, I'll stop the recording. Oh, it's weird. It's only been recording for 40 minutes. I hope not.